Okay.
Okay, so this is example 2 on lecture 12, which we didn't have time to get to in class. So this was actually using data from the open circuit test, which you see here on the left, and data from the short circuit test, which you see on the right, to find the parameters of the transformer, which I described in class. So first thing we can do is we can calculate the admittance of that excitation branch using the open circuit test, because like we said, the voltage that we measure is effectively the voltage applied across the excitation branch. And the current, obviously, since the secondary winding is open circuited, has to be the current through the excitation branch. Okay? So since the excitation branch is a shunt element in parallel like this, right, we have this RC, and we have this JXM. In order to find these components, it's much easier to use the admittance rather than the impedance, because the impedance isn't linear at this point. It's a parallel combination. Okay? So to get the admittance, we could say, well, the open circuit admittance, which would be the admittance of this branch right here, is going to be equal to the conductance minus J times the susceptance. Okay? Where the conductance is the reciprocal of the resistance, and the susceptance is the reciprocal of the reactance. Okay? So, to get the admittance here, what we do is we'll take the current divided by the voltage, right? But then we give it an angle of negative cosine inverse of the power factor. It's negative because this is the admittance angle and not the impedance angle. So that's going to be cosine of the power factor. Remember, the power factor is the power divided by the apparent power, which is the voltage times the current. Okay? So whenever we put these values in here, we get 0.214 amps divided by 8,000 volts, right? And then we have the inverse cosine of 400 watts divided by 8,000 volts times 0.214 amps. Okay, now I'll come up here, and when I calculate that out, the best way to do this is calculate this in rectangular components. And when you do that, you get 0.50625 for the real component minus J, and then you have 0.402601. Okay? So this component right here is the conductance. This component right here is the susceptance. So you can see the conductance is very, very low. The susceptance is very, very low. This is what we expected. We were saying in this test, the reason why we can do this is because this impedance has to be so high, right? If it wasn't that high, we wouldn't be able to do this test and get accurate results. So finding out what the resistance is, we're going to divide 1 divided by the conductance. And you'll see that it's a very large resistance, and we end up getting about 160 kilo ohms. Okay? For the susceptance, or the reactance, we divide 1 divided by the susceptance, and we get 38.4 kilo ohms reactive. Okay? Alright, so that takes care of the excitation branch. Now we use the short circuit data in a similar way to find the rest of the circuit, right? So remember, we couldn't find the primary and secondary components, but what we can find is a combined value. What is the primary plus the secondary referred to the primary side? We can find this, right? We can find this because we know the voltage applied right here is VSC. The current flowing through here is ISC, because this is short circuited here. Okay, so doing the same thing, we're going to use these values, and we're going to say, well, that ZSC is going to be equal to REQ plus J XEQ, okay? And this is going to be equal to VOC divided by, or sorry, that should be SC there. VSC divided by ISC, angle of cosine inverse of PSC divided by VSC ISC. Okay? And when we do that, we get 489 volts divided by 2.5 amps, cosine inverse of 240 watts divided by 489 times 2.5. And using that, we get 38.4 plus J 191.8 ohms, right? So this means REQ, which is equal to the primary plus the turns ratio squared times the secondary resistance, is equal to 38.4 ohms. And then XEQ, which is equal to primary leakage plus the secondary leakage squared, is equal to 191.8 ohms reactive. Now, as you can see, we can't really find out what each one of these are, right? Because we just have the combined value, which is the equivalent. That's good. That helps us for most of our analysis of transformers. But there are certain ways that we could find this. If we wanted to find this, we could make some assumption that says, you know, the secondary resistance is roughly equal to the primary, right? So you could say then RP and RS are exactly the same. Maybe they have the same windings. There's some way you can find out the ratio of the two. And you can find out the ratio of the primary leakage and the secondary leakage. Maybe this should be secondary. Maybe the secondary leakage is, you know, 1/2 of what the primary leakage is, or you have some way to determine that. If you could find the ratio of the two, then you could solve individually. But without that, you can only find the equivalent of each of these, but that will suffice for most cases in most studies. Okay? Thank you.